Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistors, a physics perspective. This is lecture number 58 and the topic of the lecture is vertical HEMT, high electron mobility transistor, and its modeling. So the objective of this lecture is to give you an idea about GaN or the gallium nitride based switches. We will also let you know what's a gallium nitride based converter and some power devices where we will be concentrating on lateral gallium nitride based transistor and vertical gallium nitride based transistor, and breakdown voltages with thickness variation will also be taken care of. Please understand that in our previous lectures we have gone through the idea of modeling of these GaN based HEMTs. Now we are going into the GaN based switches and its converter, which is basically a gallium nitride based design. It's a 3-5 semiconductor sort of area, and it is generally used for power devices where the voltages of the range of say 300, 400, 500 volts there when you use it. So typically when we were using silicon or group 4 element, we were actually looking at low power design, and when we were actually looking into 3-5 high power devices, and various configurations of high power devices will also be shown in this objective. Gallium nitride based switches are actually a good choice for high speed devices. We already know that point because of the very fact of the mobility of the charge carriers are relatively very high for 3-5 semiconductor for the same structural configuration as a relatively the same value of silicon, which means that gallium nitride based switches typically, since it's high speed devices, they can actually switch a large amount of potential within very short period of time, right? So if you look at dV/dt, or the rate of change of voltage with respect to time t is relatively much higher in case of GaN based devices because its current is also much larger, right? The current amount of current handling capacity is high. Now since the current is high, it effectively means that the charge which it can discharge or it can charge per unit time, right, per unit time, will also be very large, and as a result you can therefore charge or discharge a large amount of electrons in a very short period of time of the order of nanoseconds, and therefore since the switching speeds depends upon the total amount of charge you discharge, the switching speeds are much higher in case of GaN based switches. Since the switching speeds are very high, they are relatively having a very high efficiency and also a very decent power performance. When I say power performance, I mean to say that the amount of power it dissipates with respect to its efficiency is relatively low, which means that the efficiency of these devices are relatively very high. Moreover, since the electron mobility is higher, these GaN devices, which is the third point, can actually operate at much higher frequencies than silicon. As I've already pointed out, why is it so? Because of its high carrier mobility, right? Low on resistance and low parasitic capacitances as compared to the same amount of silicon material which you use. So typically it can operate at much higher frequencies as compared to silicon. That's one of the basic advantages of GaN based devices, that its operating frequencies are relatively much higher as compared to silicon. Now the why is it got a high carrier mobility? That you can actually go back to basic device physics and look at the EK diagram of a 3-5 semiconductor, and you will see that its m star value is relatively small because of a steep EK diagram, right? If you plot E versus K for for this thing for silicon, and if you plot it for this thing for gallium nitride, it becomes steeper, and therefore the second derivative of this is much larger, which effectively means that my m star actually comes down, and therefore my mobility star goes down. Effective mass goes down and my mobility becomes higher. A low on resistance because of the again same reason, because of its high carrier mobility. Moreover, it's got a low parasitic capacitances because the very nature of gallium nitride devices are having a low parasitic capacitances. Now, gallium nitride allows approximately 100 to 150 times faster switching as compared to its corresponding silicon devices, which we have already seen in our previous discussion. They are useful in applications like power switches, in DC-DC converters, in AC to DC converters, and wireless power converters. Right, typical usage of GaN-based switches can be found in these regions. Now let's look at the GaN-based converter, which does a DC-DC or a AC-DC converter. Now, so GaN-based converters save lot of space in terms of area requirement for the same amount of efficiency is much better. The second part is that at the same frequency as silicon, for GaN the loss is relatively small, and therefore it increases in efficiency. If you can see this diagram, if let's look at the first diagram here, I have this loss which is basically the loss because of power dissipation, because of all those things, and we are plotting loss versus frequency for silicon as well as for gallium nitride, right? And the target efficiency, if you see, assuming that the target efficiency is same for both of the cases, uh, if you see, the plot becomes almost linear in nature, and here also it is less slope but linear in nature. And if the target efficiency is same for both silicon and gallium nitride, means gallium nitride will actually have a much higher frequency of operation as compared to that of silicon. And therefore there are two types of losses which we generally encounter in case of a GaN-based converter. The first thing is a switching loss, and the second is a conductive loss. The conductive loss is because of the IR loss, which you generally see in any of the standard devices, and it's almost the same for both silicon and gallium nitride. However, the switching losses for silicon is much larger as compared to that of GaN. So the total loss which you see, the total loss in terms of the power is basically switching loss, switching power loss, right? Power loss, and you add to that the conductive loss. Now conductive loss is basically the loss, sort of an IR drop loss, right? And it's almost relatively almost the same for both silicon and as well as for gallium nitride. However, the switching power losses are much larger in case of silicon because the currents are so small that you are not able to handle. It takes more amount of time to switch from high to low value, and therefore if you target the same efficiency of say 80%, 60% or whatever, I can operate at a higher frequency, or if I operate at the same frequency I would get a much better efficiency in case of a gallium nitride based switches. There's a low switching loss, as I discussed with you just now, for gallium nitride, and this is primarily because of the two graphs which you see at the bottom here. This is for silicon, and so we are plotting voltage, current. The yellow one is for the current and the blue one is for the voltage with respect to time t, and this is on the right hand side is for gallium nitride, right? For gallium nitride we are trying to find out the value of voltage and current with respect to time t, we are trying to find out. Now if you can see on the left and right side, the area under the graph V and I is basically the loss, right? So V into I is power, and therefore if you look, the area under the curve here is much smaller as compared to the area under the curve in case of silicon, and therefore the switching losses are relatively much larger in case of gallium nitride as compared to that of silicon. The total switching losses which you see. As you can see, as the voltage rises, let us suppose the current falls down, then basically V into I is the switching loss which you see for both silicon and gallium nitride. Now, if you look at AC-DC converter which is shown at the top diagram, The efficiency is also much better for gallium nitride as compared to that of silicon. Now let's come to GaN-based power devices, which is gallium nitride-based power devices. There are two fundamental structures which is generally being discussed when we discussed gallium nitride-based structures. One is the planar structure and is the vertical structure. Uh, uh, the planar structure, which is on the left hand side, this one is the planar structure. The current path is along a plane, right? It's along a plane. Whereas for a vertical gallium nitride based devices, the current path is actually vertical to the device dimension itself, right? So just by the nature of the current flow, we have two types of fundamental structure for gallium based power devices. The first one is basically my planar structure and the second one is a vertical structure. Let's look at the planar structure first, and you can see that this is basically a GaN substrate power device. So I have a source, I have a gate and I have a drain. This is my AlGaN barrier, aluminum gallium nitride barrier, and this is my gallium nitride channel across which the current is flowing from source to drain, right? So this red colored path which you see here is basically the current path which is flowing from source to drain and which is flowing on the gallium nitride channel. Whereas if we come to the vertical structure on the right hand side, then you will see that you have these n plus layer on both the sides. They form source and drain, and the current path is from n type substrate at the bottom through this n drift layer, and it passes through this region. So effectively, in the first case, the channel length is between source and drain. In the second case, it is actually not between source and drain, but between the n plus substrate at the bottom and the source and drain on the right hand side, depending upon the bias where you will give in this region. So both in this second case, both are referred to as source if you look very carefully, and this is the drain on the back side, on the vertical side, right? So you apply a bias on the vertical side and the current flows through the n drift layer, right? Vertical devices are sort of epitaxially grown, known as homoepitaxial grown on the gallium nitride substrate, right? Whereas the planar devices are manufactured on silicon or silicon carbide substrate. So this substrate is either silicon or silicon carbide. This is the buffer layer, and then you have this gallium nitride, and then you have an AlGaN layer. The current which is flowing through is between the AlGaN layer and the GaN layer. So it is actually flowing between these two layers, the current path, right? Now typically, as you can see here, for both the cases, both vertical as well as in lateral, the current is obviously between source and drain from both the sides, but effective channel length, if you look very carefully, is very different. The definition of the channel length is very different from the lateral GaN as well as the vertical GaN layer. First, the second thing is um, um, this n drift layer might have large amount of impurities in a vertical GaN device, which might result in a lower current flowing through a vertical GaN device as compared to a lateral gallium nitride based device. So these are the few sort of not a disadvantages but sort of explanations. So epitaxially grown GaN on silicon substrate are favored in their production because the yield is much higher in case of epitaxially grown gallium nitride, the first case. However, see, the problem is typically when you grow a device epitaxially or otherwise, there is always a lattice mismatch, right? Now, since the thermal expansion rates are different for different material, you might have stress which is built up between the two material, which might result in further lattice mismatch or disparity between the two materials. Now, because of this heavy lattice mismatch, there might be heavy dislocation in terms of there might be dislocation of the material itself. There might be defect generation throughout the gallium nitride epitaxial layer. Now, there might be also, as I discussed with you, thermal mismatch, which may cause a cracking in gallium nitride. Cracking is effectively a crack in gallium nitride during the cooling after the epitaxial process. This thermal mismatch, which typically happens is primarily when you don't properly have a buffer layer attached between the two active layers, such that the thermal expansion coefficients are not abruptly changing, but they are changing very slowly. Now, typically, as I discussed just now with you, we require a good optimization of the buffer layer, and it is very, very important to therefore optimize the buffer layer, so that we ensure that there is not very large amount of mismatch in the thermal expansion coefficients between the two materials. Now, so 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 each one of them, each one of the either vertical or epitaxially grown, have their own advantages and disadvantages, but preferred one is basically the horizontal case, which is the lateral case, is a much more favored one as compared to this one. Moreover, in case of the growth, in terms of growth process, you need to ensure that the thermal coefficients are varying in a very small fashion between point A and point B. Otherwise, there will be stress which will be developed within that material. So these are the few areas. Let us now come to lateral GaN FET. So I will have two types of channels available. One is a straight channel, and the second one is a slanted channel. So if you look at figure A, this is without slanted channel, and we have got a slanted channel. Slanted channel is, this is what I define as a slanted channel, right? So the effective length actually goes on increasing in this case. Now, if you plot drain current with respect to gate voltage for both slanted and unslanted channel, slanted channel leads to approximately 1.5 volts, approximately higher threshold voltage compared to the without slanted channel, because you can see it's shifted from approximately 1.5, around 1 to approximately 2.5, 2.6 change in this there, and as a result the threshold voltage rise is much higher in this case. So this is basically a lateral GaN transistor, and the reason why we see a large increase is basically that with the slanted channel, the effective channel length has actually become larger, right? Not only that, the effective distance of the gate from the channel is also changed as compared to the first case, right? So if the distance of the channel is much larger away from the gate, you would expect to see a larger gate voltage in order to form a channel, and that's the reason you see that your slanted channel leads to a larger threshold voltage shift, right? And this is one of the methodology by which threshold voltage shifts are generated whenever required, right? In especially in DC-DC converters and in all the switches. So this is a lateral sort of a gallium nitride based transistor which we are trying to find. Let's look one by one into the challenges of lateral GaN device. So what are the challenges LAN device? As I discussed with you, this GaN HEMTs, typically if you look at the GaN HEMTs, they are basically normally on devices. Normally on means there is already even when you don't apply a bias, there is normally a current path between source and drain, right? And this current path, you in fact you need to give an external bias to stop this current. So these are known as normally on devices. Now the bulk to drain is directly proportional to distance between the gate and the drain. Higher the distance between gate and the drain, more voltage you need to apply in order to switch it off, right? That is expected also because the electric field becomes low, and therefore you require a larger bias in order to have lesser amount of current to flow there, which in fact ensures that there is a limitation of a bulk to drain scaling, and therefore ensuring reliability. So this is one problem area where people face that there is a limitation to the VBD scaling, right? Bulk to drain scaling is always limited. Now the problem is that since the charge carriers are moving from source to drain, uh, the channel itself is highly sensitive to surface traps and buffer defects. So if you see, you have a buffer layer at the bottom, right? This is the buffer layer at the bottom. So this is the buffer layer. This is the buffer layer at the bottom. Now the property of buffer layer will affect my GaN layer as well. Now since the active layer is the GaN channel layer, any variation in the buffer layer stoichiometric configurations will result in the surface traps and buffer defects within the gallium nitride channel. There will be a large change. Now, since there is no effective p-n junction between drain and source region, so I will tell you what happens when you, since you don't have a p-n junction sort of on the source and drain region, unlike other MOS devices, it's very easy for overvoltage failure. So if you give a voltage, there will be the breakdown will occur at a much lower voltage because you don't have the depletion region effectively available on the source and drain side. So since there is an absence of p-n junction, in a sense, you effectively are able to break down at a much lower voltage, and that's the problem area of a lateral gallium nitride based device. Let's now come to a vertical gallium nitride based device, out of which we know that there are pin diodes, and then we have a vertical gallium nitride Schottky barrier diode. We have a vertical GaN transistor, and we have this current aperture vertical electron transistor, and within the vertical gallium nitride based MOSFET, we have a planar gallium nitride and we have a trench gallium nitride MOSFET. So these are the few types of vertical MOSFETs available. The first one you can see on the A type is a current aperture vertical electron, also known as cavet. The second one is a trench cavet, where we try to make it a slanted channel, right, a slanted channel, and the slanted channel actually enters into the p-type gallium nitride here, and this is a slanted channel. The third one is known as a trench MOSFET. The trench is because the gate sorts of forms a trench through the gallium nitride drift layer, and the last one is basically a fin MOSFET, right. So all the epitaxially change, all the change which you see occurs on the drift layer. So there are two types of layer. You have a GaN drift layer and you have a GaN substrate. In all the cases, if you see, there are two layers which are effectively available, drift layer and the GaN substrate layer, right. And so if you look at the leftmost figure, which is point A, you see that you will have, so the electrons will be flowing through the active layer. In the second case, it will be flowing through the active layer. However, the effective channel length is increased more, and therefore you will have relatively a larger threshold voltage for point B, which is a trench cavet device, GaN device. Then we have a trench MOSFET device. What we try to do here, I have a a source side. The drain is on the back side, so this is a vertical device, as you can see, and there is a current flowing from this direction, which happens in this case from drain to source. Same thing happens in this case, and this is the channel which flows from source to drain on this side and this side, right. Similarly, from drain to gate, and you can actually literally control all the three gates independently, and therefore all these individual devices have their individual threshold voltage characteristics. Let's look at the breakdown voltage versus thickness. On the right hand side, you will see a graph which tells you the breakdown voltage versus the drift thickness. As expected, as the drift thickness goes on increasing, the breakdown voltage also goes on increasing. However, an interesting study is that as the doping concentration goes on increasing, the breakdown voltage goes on reducing, which is expected also in a much easier fashion, because as the doping concentration increases, you have large number of carriers available. For the same thickness, you require a lower amount of breakdown voltage. Now, if you look at the triangle one, it's GaN on GaN, which is basically meaning that your substrate is your gallium nitride and the active layer is also gallium nitride, whereas the dot one which you see, or the circle, is GaN on silicon, which is basically the GaN is the active layer or gallium nitride, and silicon is the passive layer across which you are making the GaN. So silicon is basically the substrate layer. As you can see here, the triangle ones can actually handle much larger breakdown voltages, which means that gallium nitride on silicon can handle a much larger breakdown voltages compared to that of silicon. On the left hand side, if you look here, then it is basically the electric field versus the depletion width, and as you can see, the critical electric field is EC here, right, and the electric field profile is shown when the breakdown phenomena is occurring in this case. Now, the total width or the total charge here will give you the value of the electric field, the critical electric field here, and the critical electric field depends upon the width of the depletion region. It also depends upon the effective value of the relative epsilon for both the materials. So this is how you see a breakdown voltage variation with this. Let us come with the last section of our talk for this case, and this is known as a vertical fin MOSFET. What happens in this case is that you have this vertical fin. As you can see, the D part, which is basically my, if so, this is what we are talking about, vertical fin MOSFET, which we are talking about. As you can see here, we have a source here, I have a source here, I have a drain on this side, and we apply biases at this particular point, this and this, thereby individually controlling the total amount of current flowing through this region and flowing through this region. We have this aluminum oxide, which happens to be sort of a layer between the gate and the gallium layer, and since we don't use silicon dioxide because of the relative mismatch between the gallium nitride drift layer and the oxide layer, and therefore we use aluminum oxide for all practical purposes. And what we do here is that as the channel width goes on increasing, as you can see, the subthreshold slope actually becomes worse. So you can actually do a very good switching provided you are able to sustain a much lower channel width. So around 100 nanometer, you will get around 60 millivolts per decade as the subthreshold slope when you use a vertical fin MOS device. On the left hand side, if you look, you see that as you go on reducing the dimension of this dimension, you see the electric field becomes larger and larger, and what results is therefore is that if you look very carefully here, all of it becomes dark blue, which effectively means that the amount of electron density per unit area actually falls down as you reduce the dimension of the device itself, right, because of the vertical scaling of the electric field. Now, the silicon doping concentration is taken to be 2 into 10 to the power 16 per centimeter cube. Uh, Now, as the fin width, which is this one, this is the fin width, right? As the fin width actually scales down, it becomes fully depleted in nature, because you can see that becomes fully dark blue. Dark blue effectively means that it is almost devoid of any free charge carriers. And that's a good way of controlling the current flowing through the device by just changing the fin width in a sense. If you look at the middle diagram here, the middle schematic here, it shows you the variation of current density with gate to source voltage, and it is almost like a MOSFET only, obviously. But interesting point is that as the value of the fin width goes on changing from a low value to a high value, the threshold voltage changes from from a high value again to a low value, which means that if you look at 400 nanometer fin width, it sees approximately the off current is of the order of 10 to the power minus 8, which is same for all the cases almost, but the voltage is relatively much smaller as compared to that of higher fin width. So these are the few structure or few methodologies of vertical fin MOSFET, and by independently changing the fin width, drift layer dimensions, and oxide layer, aluminum oxide, I could actually design various values of the MOS devices in this case. So let me recapitulate what we did in this lecture. We looked into, first of all, what is the difference between a lateral MOS device, lateral MOS and a vertical MOS, right? Both, maybe you can have a GaN-based device, right? Lateral GaN and a vertical GaN. Then we looked into the four types of lateral GaN. Then we looked into the advantages of having lateral GaN as compared to vertical GaN, and finally we ended up having a real simulation for a fin-based MOSFET and showed to you how the depletion width actually varies the fin width actually varies the depletion within the fin structure. So this is as far as basic 3.5 material is concerned. We will start with now a 2D material in our last two lectures as far as this course is concerned. Thank you for your patient hearing.